Good evening to all of you. Welcome to the first session of the series of 2 invited talks titled Linear Groups, which is being delivered by Professor Amber Habib. This series of talks is being organized by Curry Leaf Math Club of MTTS alumni in collaboration with MTTS Trust. The invited speaker, Professor Amber Habib, is currently a professor and head of Department of Mathematics at Shiv Nadar University, School of Natural Sciences, Uttar Pradesh. Professor Amber Habib earned his PhD in mathematics from University of California, Berkeley, and integrated MS from IIT Kanpur. We are very happy to have Professor Amber Habib with us today. A warm welcome to him. Also, we have Professor A. Satyanarayana Reddy as the chair of today's session. Professor Satyanarayana Reddy is currently an associate professor in the Department of Mathematics at Shiv Nadar University, School of Natural Sciences, Uttar Pradesh. Professor Satyanarayana Reddy earned his PhD in mathematics from IIT Kanpur and Masters in Science from Andhra University. We are happy to have him as the chair of today's session. Professor Amber Habib and Professor Satyanarayana Reddy have been associated with MTTS for a very long time. Now, I would like to hand over the session to Professor Satyanarayana Reddy. So, Satya sir, over to you.
Oh, thanks, Jyoti. Yeah. So, good evening to all of you. On behalf of MTTS Trust, I welcome all of you to these wonderful series of talks, generally 2 talks, today and tomorrow. So, we appreciate Curry Leaf for this choosing this right person as well as a very nice topic. I have known Professor Amber Habib for the last 10 years. Hope continue to be in touch with him for at least another 10 years. I first met him in IIT Kanpur in 2012. That is also an MTTS summer camp. In the same year, I joined SNU as a faculty. Since then, we are colleagues. So he is very supportive to all of us, not only faculty, students, and whatnot, everyone. In these years, he has been selected for a best teacher for a few times. So the main key point which I observe in his teaching is that the democracy in the classroom. He asks questions in such a way that it motivates students to respond. Then automatically some gentle argument starts. That leads to the learning of the concepts. That is I like very much. He has been teaching in MTTS for a long time. He tries level best to be part of the program always. He's comfortably, continuously supporting and comfortably all the activities and including the Curry Leaf now, right? So this will I should this will continue forever. I should be not be between you and Professor Amber Habib. But one suggestion I want to make is that concentrate. As Professor Kumaresan says that, think along with the speaker. Okay, so what it means is that concentrate, start thinking afresh. To answer the questions, okay, as per the present situation. Do not try to recall the previous your knowledge, right? If you think along with the speaker, then it will be very effective. So best wishes to all of you for these 2 talks. I request Professor Amber Habib to take over.
Okay, so thank you, Satya, and thank you, Jyoti, and thanks to the entire Curry Leaf team for setting this up. It's really nice to have another way of interacting with MTTS and the MTTS people, faculty, students, alumni. So today's topic for me, it's a bit personal in some sense. I gave Curry Leaf a few topics to pick from, and they picked this one. So when I was a student, at the end of, I went through this integrated masters at IIT Kanpur, and at the end of the 4th year, me and a classmate, we were selected for a summer program, which was supposed to be, well, I mean, it was about Lie groups and their representation theory. And we went for this, and it was actually intended for PhD students. So it was a little traumatic for us. But it was also very educative. And we saw, I mean, what we found very interesting was that there was a subject where algebra, analysis, general topology, algebraic topology, some geometric ideas, they were all coming together and they were interacting with each other to create interesting sort of pieces of knowledge. And we were quite charmed with that. So when we came back, I mean, we continued to study that through our final year. And then when I went for my PhD at that time, I think I went there with, not a clear idea that what is it that I want to do my PhD on. I mean, many people know even through their bachelors that this is the kind of thing we like to do. I liked most things. I wasn't very sure what I was best at. I liked algebraic topology. I liked whatever I had learned of bit of differential geometry and Lie groups. And I liked function analysis quite a bit. So I went there and I started attending all the seminars. And it took a while, but ultimately there was a group working on Lie groups. And due to this earlier exposure, I ended up in that group with Joseph Wolf as my supervisor and did that. But what happened was, and some things I realized much later, that the first exposure was a very abstract exposure. And the modern subject itself lives at a fairly abstract level. Okay. And so I was learning theorems and results, and I was working like that, learning a lot of abstract things. I didn't really know my examples properly, right? And that was a big defect in my early education in the subject. And it troubles me a bit to this day. I never really learned the examples the way I should have, because I started in a certain way. Okay. And it was a while before I realized this, and it was a further amount of time till I really sort of started to understand how the subject actually emerges out of the example, right? Because I learned it the other way around, as happens with most of our education. Mostly we are taught the definitions and then the results, and examples follow the results rather than results and structure following the examples. Okay. Now, interestingly, historically also, this is more or less what happened with Lie groups. Okay. The study began with the work of Sophus Lie. He was interested in using groups to study the symmetries associated to differential equations, and to use group theory towards differential equations in the way that the algebraists already used it through Galois theory to study polynomial equations. And he started doing that, and he set it up in a very, in a surprising abstract manner. I mean, one wonders where he was getting his insights from, since he doesn't seem to have worked out that many examples. But he did a remarkable job, and he created the subject of Lie groups and Lie algebras. Okay, and it was quite a while later that John von Neumann pointed out that the whole theory, the abstract theory of Lie groups and Lie algebras, could instead, you could start understanding it in a much more concrete context of what I call the linear groups, which is what we will look at today, right? And here you can set up, the examples are easy to get into, and the basic definitions quickly make sense. You do lose a certain level of insight by giving up on the abstraction, but it's a much more pleasant introduction to the subject. And later also you benefit if these core examples, are strongly with you, if your understanding of them is strong. Okay, so that's what we will do today. We will look at these things called linear groups. Okay? And today I will concentrate on examples and motivation. Okay. Not so much on proofs of theorems. We will do some proofs, but the hardest ones we will put aside, because it doesn't make any sense to try to do them in a single lecture. But I think we will get some idea of what the subject is about, and we will reach a certain level, and then in tomorrow's lecture we will see what is the use of what we have done today. Okay. All right. So let me start sharing a pad that I can write on. And then let's start talking about these things called linear groups. Okay, and as Satya said, I don't mind questions. I mean, if you put them in the chat box, I'll probably not see them. My attention will not be on the chat box. If you raise your hand, I'll probably not see that. So feel free to just unmute and say something, okay? Just don't do it every minute, okay? And then it's my choice, right? I will respond to you as I see fit. If I don't want to answer you, I won't answer you. So simple enough for me. So feel free to interrupt and ask for some clarification. If I can give it, I'll give it. If I can't give it, I'll make some excuse or I'll try to do it later. Okay. So we are going to talk about these things called linear groups. Now you see what happens is when you study algebra and you study group theory as your first serious algebra, what kind of groups do you end up looking at, right? So right away you look first, say, at permutation groups or the cyclic groups, the dihedral groups. So things are given to you as some certain abstract elements with some relationships, right? With some multiplication table or rules for combining them. And then you do other constructions to create more complicated examples, right? Semi-direct product, quotient, etc., etc. Okay. Now, one kind of example that doesn't get generally the importance it should are groups made out of matrices, and that is really what we are going to be looking at today. Okay, so let's introduce the notation for that. Now, this could be, some of this could be done over any field, but most of it can only be done, what I would do today can only be done over real numbers or complex numbers. And just to simplify, and I'm just going to work with real numbers today, all right? So the field that we will work with today will just be the real numbers. Okay, don't really like red. I don't know how it got selected. Let's select blue. C will also do generally, could be either. But then sometimes I'll have to say if it's real, do this, if it's complex, do that, and I don't want to bother with that in this first lecture. Okay, all right, so that's the field we will work with. Now, what do we have? So for instance, we could work with n cross n matrices. So those I'll call MNR, or maybe just MN, since I'm only going to be working with real numbers today. Okay, so n cross n real matrices. Of course, these become a group in an easy way if you use matrix addition, right? So matrix addition makes these an abelian group. But they're not a very interesting group, right? It's just n cross n matrix can just be seen as a vector with n square entries. And so it's really n square dimensional vector space, and you're just using ordinary vector addition component wise. So not such a big deal. What's much more interesting is if you try matrix multiplication. Okay. Okay, so let's see what happens if you multiply matrices, right? So I mean, it's fine, but this is boring. So let's try matrix multiplication. Okay. Now, what are the properties, right, associated to this binary operation on n cross n matrices? Certainly, it is a binary operation, meaning you do have closure. If you multiply two n cross n matrices, you will get an n cross n matrix. The multiplication is associative, so that's also good. There's an identity, which is just the identity matrix, so that's also fine. We are starting to see some of the things we would want in a group. One thing is left, which is inverse. But then, of course, you know that this does not work out, right? There are matrices which don't have an inverse under multiplication. Okay. So what do we do? Well, the simple solution is just throw out the ones which are causing trouble. So throw out the ones which don't have inverses and simply keep the ones which do have an inverse. Okay. So that's what we will do. And that set will be called GLNR. Or again, since I'm only going to work with real numbers today, I may just call it GLN. Okay. And these are all the n cross n matrices which are invertible. Okay. And you know that one way to test whether a matrix is invertible or not is to look at its determinant. So these are the matrices whose determinant is not zero. Okay. All right, so how about these? Do these form a group, right? And one can quickly check, yes, if you multiply two invertible matrices, then that's invertible. Through the determinant characterization, you could see that. Associativity is already there, identity, because identity matrix is invertible. And of course, now everything has an inverse, right? So this is a group, and we will, and the name for this is general linear group. Okay, and that is why the notation for it is GL, for general linear. Okay, so for instance, that will be one of the groups that we would like to talk about under this subject of linear groups. Okay, now again, this is just algebra. As I said, we want to go beyond and look at other aspects. Now, because of this concrete example, it doesn't just have algebra going on. It has other things going on. And for instance, you can talk about matrices being near or far from each other. You can talk of the size of the magnitude of a matrix in some way, right? And so that way, you know, some metric space aspects can come in. You know, you can discuss limits and sums and series and things like that. So therefore, you have some analysis going on as well with these groups. So algebra and analysis would get a chance to interact with each other in this setting. Okay. All right, let's just set that up, right? So let's just put up the metric. I'm sure this is familiar to many of you, but let's just do it once. So and the metric can be put in on all of Mn in the first place. So if you have an n cross n square matrix, real entries, you define what is called its operator norm. Now there are many different ways of creating something, some notion of the magnitude of a matrix, and this is one of them. Different ones are convenient in different settings, and this one is convenient in our setting. Okay. So you must have seen this before. What is the operator norm? So you basically ask how much stretching can this matrix do? So you have a square matrix, and what you can do with it is you can take an n-dimensional vector, you can multiply it by this matrix, get a new vector, and generally the new vector will be something completely different. It will point in a different direction, its length will be different. And what the operator norm looks at is how much the matrix can stretch a vector, right? And some vectors it might shrink, some it might expand. What is the maximum expansion that it can cause? All right, so how do you set it up? You say I will take the supremum, okay, of this set. Okay, you look at the length of a vector. Now this is the Euclidean norm. You're working in Rn, so this is standard length of a vector, right? And you ask what is the ratio between the image and between the image and the original vector, right? And so of course, to do this, you need your vector not to be the zero vector. Okay, so it needs to be like this. Okay. Of course, one question immediate is this supremum attained or not, right? Is it a maximum? So here it's easy to see some things. First, suppose I only looked at unit vectors. Okay. Then this norm x would become 1, and so this ratio would simply become norm ax. The overall set stays the same because any ratio you had from a particular x, you just normalize that x to be a unit vector, and that ratio would show up in the second set. The advantage of doing that is that the collection of vectors whose norm is 1, right? This is basically a sphere in your Euclidean space, and so this is a compact set. And over this compact set, for each member x, you're looking at a number, and that number is created by a continuous function because linear maps are continuous, and taking the length preserves that continuity. And you know that supremum is attained in such situations. So this will actually be a max. It will actually occur for some x. Okay, so for some work related to the operator norm, it can be useful to know that it will actually occur through a particular x. Now, what are the basic properties of this operator norm? Here are some obvious things. Well, some are obvious, some not so obvious, but all of them are fairly easily checked. So I won't do that today. I just want to list these. For instance, all these ratios are, of course, non-negative numbers, and so the supremum is a non-negative number. So it's clear that norm A will always be greater than or equal to 0. Can it be 0? So let's see. Right, let's look at any of these. Now, suppose the norm was 0, then right, for any unit vector, your norm Ax would have to be 0, right? The only way the supremum can be 0, you have a set of non-negative numbers. The only way the supremum can be 0 is if all the members are 0. So all these Ax's would have to be 0. And the only way that all the Ax's can be 0 is if A itself is the 0 matrix. So the operator norm can only be 0 for the 0 matrix. Okay. Another thing is that what happens if you were to scale the matrix by a real number? Okay, now, if A did some amount of stretching, then TA would do T times that much stretching, right? And so it would simply be mod T times norm A. So that's also easy. Okay. Now, other interesting things are that you do have the triangle inequality. And what the extra nice thing about this norm compared to some other norms is that you also have a sort of triangle inequality for matrix multiplication, not just for addition. Okay. Now, out of all these things, and I'll need these at certain points of today's lecture, but if you leave out the fourth, right, and look at this, then this is generally what you consider to be a norm on a vector space. Mn is a vector space, and so this operator norm is a norm. Okay. And once you have a norm, you can use it to put a metric, right? So you can define DAB to be norm A minus B, and this becomes a metric on the n cross n matrices. So now your n cross n matrices are a metric space, meaning you can talk about a sequence of matrices approaching another one, right? You can talk of, if you have a function defined on matrices, you can talk about whether that function is continuous or not. You might even be able to discuss differentiation, etc. Okay, so all that is open to us now. Okay. For example, okay, let's just start putting this to work. So look at determinant. Right? Determinant is a map from n cross n matrices to real numbers. Okay. Now, one of the things that is true that I should observe is that Mn is a finite dimensional vector space. On finite dimensional vector space, it is true that all norms are equivalent, which means that the concept of limit that one norm gives you will be the same as the concept of limit from any other norm on the same finite dimensional vector space. Okay, so in some sense, it doesn't really matter which norm you work with, you will get the same abstract results. If a function is continuous with respect to one norm, it will be continuous with respect to any of the other norms on that. Okay, and here it also means that if you had say a sequence of matrices and you wanted to know under the operator norm if they are converging to a particular matrix, you simply need to look at the individual entries and whether they converge or not. Okay. Now, if you have this viewpoint, then it's pretty clear that determinant is a continuous function.
Sir, is it domain?
What happened? Oh, sorry, my mind was still in metric.
Yeah.
Thank you, sir. These are the things that happen. Okay, thanks so much. That's why one needs an audience. When it's much worse when I tape records on my own and then share with students because there is no student to correct what I am doing. All right, good. Now we are in better shape. All right, so we have determinant. Of course, you take an n cross n matrix, you get a real number. Why is it continuous? Because how do you compute determinant? It's just various additions, multiplications, subtractions, and so all those are continuous. Now, what are some consequences for us? For example, look at GLNR. Okay. Remember that these are the matrices, n cross n matrices whose determinant is not zero. In other words, this is the pre-image under determinant of the number 0. Okay. Sorry, the complement of 0. All right. Now, this, of course, is an open set in R. And you have its pre-image under a continuous map, then that pre-image will be open as well. So this tells us that the invertible matrices are an open subset of the n cross n matrices. Right? Okay. All right, let's look at another thing. Let's look at all the matrices whose determinant is 1. Again, you can easily check that this is closed under matrix multiplication, and if A is present, then A inverse is present, etc., etc. This is also a group as well. Okay, but now what is it? This is the pre-image of the single number 1, right? All the ones whose determinant is exactly 1. And singletons are closed. This single point set is closed in the real numbers. And that will tell me that this SLN is closed wherever you look at. So you could look at it as a subset of GLNR and then do this, or as a subset of MN. Doesn't matter where you look, it's closed in that. Okay. And by the way, this has a name. This is called the special linear group. Now this, just as a side comment, these are extremely important groups. Okay, a lot of the modern theory of related to such things was created by first looking at the examples of 2 cross 2 real matrices with determinant 1 and also the complex version of that 2. And it's amazing how important these are and how intricate their role can be in different contexts. Okay. And they were first looked at because related groups came up in quantum mechanics. And then people realized that to understand those groups, they should first look in the simplest situation of SL2R and SL2C. And then these themselves turned out to be quite complicated. Only the modern theory for these was only created in the late 1940s and early 1950s. And it has a special connection to India because after Ramanujan, our most famous mathematician is Harish Chandra. And Harish Chandra, in fact, started his career with some publication on the representation theory of SL2R. Okay. And then he went on from there to a very general study of this and many related groups. Okay. Okay. All right. So we've just been doing some little things, nothing very complicated yet. We have a couple of examples of matrices, but we can see that although the definition is through algebra, but already topology, metric space kind of discussions are starting to show up a bit. At least they're already there in terms of what is the overall nature of this set, right? It's more than just something with algebra. One of them is an open set, the other one is a closed set. Okay, so this will lead to our definition. Here is a definition. A matrix group. Okay, now you might think a matrix group is a group made of matrices. And while that is true, we will actually demand something more. We will demand that it be a closed subgroup of GLNR. Okay, so that is special. We don't, we'll see later why this is a useful requirement. It's also, anyway, I think it's too early for me to make comments about that. A matrix group is a closed subgroup of GLNR. We've already seen a couple. GLNR itself is of course closed in it, and SLNR we have seen is closed in it. What other kind of groups can we create? Here's one that we can create easily. Look at the orthogonal matrices. Okay. All right. Okay. Is this closed? Is this open? Can we create some function and view ON as the preimage of that function, of some set under that function? Look at what we did with GLNR or SLNR. In fact, SLNR is probably the right thing to look at, right? Something equal to 1, something equal to identity. This is looking a bit similar. Can you suggest what I can do here to see it as a preimage under some function of something?
Sir, good evening, sir.
Yeah.
Sir, can we use the determinant function?
Well, I mean, you certainly can, but see, determinant gives you real numbers, right?
Because
so which
orthogonal
real
matrices,
numbers preimage would you look at? Now, if you look at preimage of say 1, you will get the full SLNR.
sir, can we take plus and minus 1?
Okay, but then you will get all matrices with determinant 1 or minus 1.
Okay.
Now that will contain these, right? I think what you have in mind is the result that if a matrix is orthogonal, then its determinant is 1 or minus 1.
Yes, sir.
Okay, but remember, that's not the full story about orthogonal, right? Having determinant 1 doesn't make a matrix orthogonal necessarily.
Oh, okay, sir.
Okay. Yeah, okay, good try. And so we learned something from it. But look at the definition, try to make something happen from this definition. I'm going to say I want some function phi and p-image of something. You are going to tell me what phi to take. Look at what we did here and now look again at what the situation is. Some of you have probably seen this before and therefore are feeling shy that it's not right to say something we already know. Well, don't worry, now you can say it, okay? Even if you have seen this before, just say it so that we can proceed.
A goes to A transpose A.
Excellent. Okay. So, and I take the p-image of what?
Identity.
Identity. Okay. So what does phi do? Phi is a map from ON. Okay. To wherever. Okay. What it does is it sends a, I mean, not ON, of course, from GLN. And let's say to GLN again. Okay. What does it do? It sends A to A transpose A. Okay. All right. So A is invertible, then A transpose is invertible. The product is invertible. So this is fine. Or you could even take Mn if you don't want to think that much. But here the function is continuous because, again, in this matrix multiplication, all that's happening is addition and multiplication. So this is a continuous map. And of course, the pre-image under identity is exactly these things for whom A transpose A is identity. And so that is ON. And so therefore, what can I say about ON? It will be closed, right? Because a single point set is always closed. And so the p-image under a continuous function will be closed. This is again a closed subgroup of GLN, and therefore this is a matrix group. Let me do one more. SON, special orthogonal group. These are all the matrices which are orthogonal and whose determinant is 1, right? Because as we were told, determinant could be 1 or -1. So just keep the ones with determinant 1. All right, that's again a subgroup of GLNR. Is it closed, open? Can we say? Sorry, somebody was saying something.
A transpose A equal to identity.
Equal to identity. Okay. Thanks. Right. Now what happens? Can you connect it with things that we have already done?
It's the intersection of those sets.
Good. Right. So there's just the orthogonal ones, right? The ones which are both orthogonal and have determinant 1, right? It's just this intersection. These are both closed, so this is closed. There are many more such examples that one can create, but today let's stick with these, and we will work out some calculations for these as we go. Okay. Now these are very direct. These were actual matrices, and we just checked that the group that they form is closed. It could also happen that you have a group which is not initially made of matrices, but maybe it's isomorphic to something made of matrices and can be then seen as a closed subgroup. Okay. So that it's always good to do that because many things you want to know what's happening up to isomorphism. So therefore, let's set up a definition like that. And this is what will be a linear group. The linear groups that we had in our title, a linear group is a group which is isomorphic, okay, to a matrix group. The thing is, there may be a group which initially is not made out of matrices with multiplication, but is something else. But through some map, you are able to view it as made of matrices under multiplication. Okay. Here's a simple enough example. Okay. So suppose I look at real numbers, full set with addition, right? Now, it's not directly, while real numbers can be seen as 1 cross n matrices, 1 cross 1 matrices, but the operation doesn't match, right? So it's not directly a matrix group. Okay. But what you can do is you can match it with matrices that look like this, with ones on the diagonal and some entry here. Okay. Now these are 2 cross 2 matrices. This is a closed subgroup of GL2R. Okay. And when you multiply two of them, just do it in your head. So 1x01 multiplied with 1y01. And you will see that off diagonal below stays as 0. The diagonal entries stay as 1. And if you look at this corner entry, so when you multiply 1x with y1, what will happen is you will get x plus y, right? And so this is matching up with the addition over here, right? So x going to 1x01 is the isomorphism, right? So it could happen that a matrix initially is not looking, a group is initially not a matrix group, but you can convert it into one. And so that's perfectly fine. And these are what we will call linear groups. Okay. Okay, now you would want to set up your usual thing, right? What is a subgroup? What is a homomorphism? But within this context. And what that means is always taking care about to make sure that whatever you are getting will finally match not just any subgroup of matrices, but a closed subgroup. Okay. So for example, if I have a matrix group G, and H is a subgroup, okay. Right now, that is not enough for me to call it a matrix subgroup, because if it's just any old subgroup, now G sits inside some GLN, and so through that H sits in GLN. But why should H be closed, right? And so the way to make sure that things work out is to demand that H is closed in G. Okay. So we will say that this is a matrix subgroup of G if H is closed. Right? So it's a subgroup and it's closed, then we will call it a matrix subgroup. Okay. Now, similarly, suppose I had two matrix groups and I had what would I mean by a homomorphism between them? Okay. So suppose GH are matrix groups. And I have a map between them. When would I say that this is a homomorphism of matrix groups? Okay, so this is the whole term, homomorphism of matrix groups. Of course, I mean, they are groups, so it better be a group homomorphism. But then there is more to these groups. They are all metric spaces, right? Right? They're subsets of a metric space, so they're metric spaces themselves. And therefore, I don't just want to study any old maps. I want to study continuous ones. Now, this phi will create two subgroups, right? Any homomorphism creates two subgroups. The kernel and the image. Naturally, I want those to fit in my structure. So I want the kernel of this phi and the image of this phi to be matrix groups. What assumption should I introduce so that those things happen? Well, only that the image is closed, I just have to say it directly. So that just has to be a requirement I put down. So phi G is closed in H. That will make phi G a matrix group in its own right. Okay, so let's note these consequences. Then phi G is a matrix subgroup of H. Okay. What about the kernel of phi? It is certainly a subgroup of G. Is it a closed subgroup? Okay, so what is kernel? It's the pre-image of the identity, right? And therefore, due to continuity of phi, things will work. Okay. Okay, so these conditions, the continuity and phi G being closed, make sure that all the groups you will create doing your standard constructions and things will stay in the collection that you want to talk about, the matrix groups. Okay. Okay, and therefore in particular, one thing that will happen is if you have, right, remember that if you have G and you have the kernel, right, what is this going to be isomorphic to? This is going to be isomorphic to phi G. I mean, that's always going to be the case. And so this itself is it's isomorphic to a matrix group. So therefore, this is a linear group. Okay. Now the kernel is a normal subgroup of G, right? In this case, it's a closed normal subgroup of G. So the natural question that arises, and this is an important question from the viewpoint of later work, right? You will sometimes be quotienting, sometimes be taking images, etc., etc. You were starting with some matrix groups and you did something. Do you still have a matrix group? So the natural question is, suppose N is a normal subgroup of G. Okay, G is a matrix group. N is closed in G. So all the possible good things are there. Now I can quotient. And what am I worried about? Whether this will stay in the right class, right? In the class of matrix groups. Meaning, is this a linear group? Is it isomorphic to a matrix group? Okay. And as we will see, probably not today, but most likely tomorrow. I mean, actually wasn't clear how much I would be able to do today. I would expect is that this would finish tomorrow. So the answer is no, okay? So there's an example, not very complicated. I mean, the groups are not complicated, but the reasoning involves building up a good amount of knowledge. I mean, these are always the trickiest questions. That you have an object of one type and you show that there is something that you can't do with it, right? It's generally, if you want to show something can be done with it, well, you just show how to do it, but how do you show that something can't be done with it? In this case, one is asking, show that there is no, no isomorphism with the matrix group. Now, how do you even talk about such a thing? Okay, that means we have to develop our understanding of matrix groups much more before we can actually come back and resolve questions like this. So there's a question that occurs right at the start, but it can't be answered at the start of the study. We'll need to develop some machinery, some knowledge before we can come back and give example of this. Okay. So anyway, that is one of the defects of this. It does tell us that, as we will see, you can do a lot of nice things with matrix groups. but it is not a collection that is in some sense closed under all the things that you want to do with groups. And so even to study matrix groups, you actually need a more abstract setting inside which everything can happen. So you do need the abstract Lie groups finally, okay? But still it is better not to go for that straight away and to first develop our understanding of this. It's good also to know why it's necessary to go to a more abstract setup. Okay. All right, now the next, all right, and so the example will come later. Here's another question. Since matrix groups are metric spaces, that means things like continuity can be used to exploit our study of them, right? So you can have notion of limits and continuity, etc., associated with them. Okay. Can we also go beyond limits and continuity to calculus? Can we, for example, talk about if I have a function on some matrix group, can I talk about differentiating that function? Okay. And if I can, then what use is that? Can it be used to tell me something about the algebra of the group? And this is one of the fun things. So this is what I'll try to develop some of this in the remainder of today's talk. Okay, we'll see a bit of what it could mean to do calculus with matrix groups. And in fact, that is the extra knowledge and structure that we will need to come back and answer this little question that I have posed here. So this business of being able to do calculus on matrix groups, what it's going to do for us is something very interesting. It's going to become a technique for converting group theory questions into linear algebra questions. Okay. And linear algebra, okay, at least to me, is something simpler. I mean, I'm not Satya, I don't know my groups that well. So, I'm more happy computing some eigenvectors, eigenvalues, adding, multiplying matrices. And so for people like me, this becomes, something that we feel, okay, this is what we can do, okay, with groups. All right. Okay, so let's see what we can do here. Now the point is that matrix groups are so concrete because they're basically living inside Euclidean space, right? Any matrix group is made of n cross n matrices, so it's living in an n square dimensional Euclidean space. We know what calculus means there. All we have to do is restrict that calculus to the matrix group. Okay. So imagine some Euclidean space. I can't really draw an Rn square. I mean, Rn square has to be one-dimensional or then four-dimensional or one-dimensional is useless to draw. You don't get any insights. So I'll draw R3 and we'll pretend that this is actually R4 or R9. Okay. And there is some subset of this, which is my matrix group, right? Some G. Okay. Now take a point here. Okay. And let's ask something like, what could we mean by having a tangent vector to this shape at this point, right? What could we mean by having a tangent vector? So what could it mean? Right. Now, what you do in calculus is, that to talk about things like tangent vectors, what you need are curves. So if you have a differentiable curve in Euclidean space, right, you can differentiate that and you will get a vector, and that is what you consider as a tangent vector. So to get a tangent vector at A, what we need is, we need a curve, meaning we need a smooth map starting from some interval and mapping into G. And let's say C1, meaning differentiable and the derivative is continuous. Okay, so this will have some image, just denoted by sigma. This will have some image in G. We need it to pass through A. So in fact, let's make sure that we pass through A at 0. Okay. And if I have such a curve, then what I get on differentiating it will be called a tangent vector at A. Okay, as I have drawn. And then of course, you could have many different curves through this point, and they will all generate their own tangent vectors. So you could have many tangent vectors at A. Okay. And we will call that TAG. This will be the tangent space to G at A, right, consisting of all such tangent vectors. Okay. Now, right. Now, in particular, we'll be interested in TIG, right? The tangent space at identity. We'll really concentrate at this one. Okay. Something, let me just say it briefly, is that if you understand what's happening in a group around identity, then you know what's happening elsewhere, because you take, what's happening at identity and you multiply by a fixed group element, and everything just shifts over to some other location, and then you know what's happening there. Okay. So while we can define the tangent space at any point, but really, if you understand it in one place for a group, then you understand it everywhere. And so we will concentrate really on the tangent space at the identity element, right? And that will make our calculation simpler. So that's the game. Okay. Now, we are accustomed to things like this. You have a curve, you have a tangent line, you have the graph of a function, you have a tangent plane, right? Now, this is something more abstract. I mean, this is some subset, and you again have something called tangent vectors, or they could point in any old way. So one obvious question is, we are accustomed to tangent vectors kind of lining up nicely, right? In this case, forming a simple line or forming a plane. Right? So the natural question is, this tangent space, is it a vector space, right? If I take two tangent vectors and add them, or do I again get a tangent vector? If I scale a tangent vector, do I again get a tangent vector? Okay. So luckily this is true, otherwise we wouldn't get very far. So TIG is a vector space. Okay. Right now, scaling is simple enough. Right, so one question is, suppose you had a tangent vector, then would twice of that tangent vector be a tangent vector? So do I have closure under scalar multiplication? Now I'm going to make a comment. I'm going to say this is easy to show. Okay, and I just give, I just wave my hand and say, see what happens. Suppose you have a tangent vector, right? So what is it? It's coming by differentiating a certain curve. Some sigma t, when you differentiate, you get that tangent vector. I want to create, let us say, twice that vector by again differentiating a certain curve. So do I have to create a new curve? Well, yes. I mean, I want something whose derivative is a different vector, but I use the old curve. What you do is travel along the same curve, but travel twice as fast. So for example, simply take sigma of 2t. right? And that's a new curve. You will move on the same path, so the tangent direction is the same. But now because you are moving twice as fast, the tangent vector will be twice as long. Okay, so that way it's easy to see that the space of tangent vectors is closed under scaling. The tricky part is it closed under addition? So if I have two tangent directions, right, say x and y, is x plus y also a tangent direction? Okay, well, let's take two curves, right, which would each create a tangent vector. So let's take two curves, alpha, beta, from some interval, which I can take to be a common interval for them, C1 into G, such that alpha 0 and beta 0 are both identity. Okay. And then alpha dot 0 is a tangent vector, let it be x. Beta dot 0 is a tangent vector, let it be y. So the question is, what about x plus y? Can I create a curve which will create the tangent vector x plus y? And I'm just going to give you a certain formula and we can just check that it works. So we'll use these alpha and beta and combine them in a certain way to see that things will work. Okay. All right, so here is the curve that we will take. Okay. So take alpha t and A inverse and beta t. How do you motivate this? Well, the idea is, differentiation as the product rule. So if you want to create a sum by differentiating, you should start with a product. So that way it's natural to think of trying at least alpha t, beta t. But alpha t, beta t by itself don't pass to the right point. For example, at t equal to 0, alpha 0 times beta 0 would be a square, would be I square. Okay, okay, this was actually a more general argument. Let me remove this A inverse. I don't need it. Okay. All right, because I, in my mind, had prepared a TAG is a vector space, and then while talking to you, I decided to do only TIG. So let's just take alpha t, beta t, and okay, so the motivation is simple. Right, product rule would convert product to sum. So start with a product, so that on differentiating you get a sum. Right? Okay. So what would be alpha dot t? Product rule works for multiplying matrix functions as it does for normal ones. So you'd have alpha dot t, beta t plus alpha t, beta dot t. Okay. And therefore, if you took sigma dot 0, you would get alpha dot 0, that is x. You would get beta 0, that is identity. Alpha 0, that's identity. Beta dot 0, which is y. And so you get x plus y. And of course, let's also note that it's happening at the right point. Sigma 0 is, of course, alpha 0, beta 0. So I times I is I, right? So got a curve passing through the right point, creating the right tangent vector. Okay, good. So every group has associated to it tangent spaces at all its points, which turned out to be metric group, and these turned out to be vector spaces. And in particular, the vector, the tangent space at identity, which is the one we'll concentrate on, turns out to be a vector space. Okay. Now, in calculus, what is the role of tangent spaces, right? One sort of philosophical thing is that if you say have a graph of a function and you find the tangent line, what is the role? The role is that for values of the function close to this region, the tangent line is a good approximation to the function. So this is a starting point for approximating the function by simpler things, right? So you use a linear approximation to the function coming about from the tangent line. Similarly, if you had a function of two variables, you would have some graph like this, and you would have a tangent plane. And again, the idea is that for a small portion, this tangent plane would stick very close to the graph and could be used as an approximation to the graph. It would give you linear approximations to what is really happening. And we basically have the same idea here. Through the tangent space, we will try to get linear approximations to whatever is happening in the group. For example, things happening with the group operations. And the linear thing would be easier for us to compute, and that is what we would then work with. Okay. So let's just see, so for example, take R with 0 removed, right? And so that's a group. I'll call that R cross. I have removed 0, and I'm looking at it as a group under multiplication, right? Now it's clear that if I look at what the tangent space should be, right? The tangent directions are just like this. So the tangent space should simply be a line like so, right? And it's supposed to be a vector space, as we have already proved. Okay, so it's some line associated to this like that. Okay. All right, so that's, in this case, so that's my group R cross, and this is the tangent space at identity, which is just going to be R with the addition, right? It's a vector space, right? Okay. Do we know any nice way to go back and forth between real numbers with addition and real numbers with multiplication? But that's what we want to build up. Some nice way of going between the tangent space and the original group. Do you know a nice way to move back and forth between all real numbers and the non-zero real numbers with and matching the operations of addition and multiplication?
Exponential.
The exponential, right? Okay. So remember that exponential will take me from real numbers with this to positive real numbers. So it won't take me to all of R cross. It will only take me to the positive ones, right? But the good thing is that it's a homomorphism. So that's one good thing about it. So it connects the vector space operation with the group operation. What's the other good thing about it? That it's continuous both ways, right? So it's continuous from R to R cross, and the inverse is the log, and that's also continuous, right? So it's what we would call a homeomorphism. It's both this and its inverse are homeomorphic. So there's also an inverse, right? So S goes from one to the other, log goes the other. Of course, this is too simple an example. Many nice things happen here. We can't expect all of them to hold in general. Let's take something a bit more complicated, but not too complicated. So now let's look at the circle. Okay. So this is S1, right? I mean, just the unit circle in R2. And how do you see it as a matrix group? You can see it as, how are points located? Through the angle theta with the horizontal. That's one way to think of these points. And you can therefore think of each point as corresponding to a rotation by an angle theta. And you know how to think about those as matrices, right? These are the rotation matrices for angle theta, right? Okay. So that's what, so this is a matrix group. I mean, the circle you can see as this set. Okay. Now here is one or corresponding to the identity matrix, right? Okay. So that's the identity. Now again, clearly there are two tangent directions. I mean, there's one tangent direction, right? You can view tangents like this. For this part, I just want to draw pictures. So again, you would have a tangent line. Okay, let me draw it in red to match what we already had. Okay. Right, so this is my G, which is S1, and this is my tangent space at identity, which is again real numbers with addition. Okay. Again, I want a way. Is there a way to go back and forth, right? Like you had here this exponential map. Could there be a map from this tangent line to this group?
E power IT.
Yeah, so we have already basically given that map here, right? Okay. So you can have this map T going to, well, right now I will take cos T minus, okay, sorry, not instead of theta, let me write T. This is a map from the tangent space at identity to the group. Okay, and I think someone was suggesting EIT. Yeah, you can do that also. To do that, and let's do that because maybe it will give us another hint. That this could also be seen as the unit circle in the complex plane, right? And then the points on the circle are points of the form EIT. So another way to do that is to say that send T to EIT, okay, viewing the circle as sitting inside C, okay, which is interesting because it's again the exponential map which has come into play, right, just like it did here. Okay. All right, so somehow the exponential map seems important. It's not, I mean, it's still, what are the nice properties that are preserved? It's still a homomorphism. Now this one was only on part, but this one will go round and round the whole circle. What will be lost in this case is 1, 1. But what will be true is that if you took some portion around origin, which was not too big, then you wouldn't go a full circle, you would only cover part. And for that part, you would have an exact identification between the two. So this is what one would call a local homeomorphism at 0, meaning there is an interval around 0 in the tangent space and an interval around identity in the group, which are homeomorphic under this map. So even though you don't have it for the full spaces, but you have it locally. Okay. And in a group, if you can get local information around identity, that's good because you can move it around by translating, right? So that is a useful thing to have. But what this suggests, you know, these two examples is that somehow exponential is a useful thing to look at. So let's take an abstract look at that. 7:15. Okay, so when should I stop?
Kaveri.
I should stop already, or I should stop in a couple of minutes.
Yeah,
No,
Kaveri.
sir, you can take time.
Yeah, okay, I'll take, let me just think this through. I don't want to stretch it too much more. Okay, so let me at least introduce the exponential map and a few little things about it. Okay. So the thing is, we want to do this, but now we don't want to do it working with numbers, right? We want to do it working with matrices. So what we need is some notion of exponential of a matrix. Okay, so we write it as x perf a or e to the a. Now what do? We need some definition of exponential which is easy to generalize. So the one which is easy to generalize to this context is the one through power series. So e to the x, if you define through power series, right, sigma x to the n by n factorial, that is something that would make sense in our context as well. So we take this to be the definition. A to the n makes sense, dividing by n factorial makes sense. Since you have a norm, right, you can ask whether the partial sums converge. Okay, and basically, you know, I just want to say that all those things work, and one can show that this is a convergent series in the usual senses. Okay, and you have this map which is defined like this. And in fact, it's not complicated. You just take the proofs for e to the x or e to the z and its convergence. And they more or less directly give you the proof for the convergence of e to the a for a matrix A as well. In fact, this is where the observation that norm AB is less than equal to norm A, norm B would be helpful. Okay. Let's compute some of these, okay? So, for example, let's just do some 2 by 2. And suppose I had A and 0 and 0 and B, and I set out to exponentiate this. So you'd have to first, n equal to 0 would be a to the 0. So that by convention means identity. So the first term is always identity. Next term is a itself. Next term is the square, but divided by 2 factorial. Next would be the cube divided by 3 factorial, etc. Now you see that these off-diagonal terms are always 0, so they will therefore sum up to 0. And then the top diagonal term 1 plus a square by 2 factorial, and then a cube by 3 factorial. So you can see it's just turning out to be the exponential of a. And similarly here you will get the exponential of b. Okay. All right, so diagonal matrices will always be easy to exponentiate. It will simply be the exponentials of all the individual diagonal entries. Okay. What would happen if it was a bit more complicated? Suppose it was a and then some x and then some 0 and then some b, and I took exponential. Well, okay, first 2 terms are simply identity and the matrix itself. But next time you will have 1 by 2 factorial and the square of the matrix. Right, let's just do the squaring. So you'll have ax with a0, so you'll get an a squared. Okay, and then 0, and then below it 0b with a0, that will give you a 0. Over here, ax with xb will give you a plus bx, right? Will give you an ax and a bx, I think. And then finally for this corner, 0b with xb will give you a b square, and similar. Now again, you can see always here a 0. And then in this again, 1a square by 2 factorial. And if you do the next term, you will see that again it's matching up with e to the a. And again here it's matching. Over here, something more complicated is happening. Let's not even try to sort it out. Okay, something will come here. That's all. Let's leave it at that. But the interesting thing is that even though this was a more complicated matrix, on the diagonal, I still got the exponentials. So in general, it's what the lesson is, that if you have say an upper triangular matrix and you exponentiate it, the top part may be a mess, but the diagonal will at least be easy. It will simply be the exponentials of the individual matrices. Okay. And one more, just to have it in place for something I will want to say tomorrow. Okay. So let's take something where things are not diagonal. So for instance, let's take something of this type. Okay. And let's exponentiate it. We have 1, 0, 0, 1. We have this matrix again. Okay. You have its square. What will happen? So first row times first column minus t squared. First row times second column 0. Right. Second row times first column 0. And then this times this, again a minus t squared, right? Okay. Let's do one more. Hopefully enough of the pattern will be visible so that we can see what's going on here. And then we will try to reach some conclusion. Okay, so now I have to multiply the matrix with its square, right, to get the cube. So 0 minus t with this, now I'll have a 0 here. And then 0 minus t with this, I'll have a t cube here. I'll have a minus t cube here. I'll have a 0 here. Okay. Okay, so now let's look at the 1, 1 entry. I've got 1 minus, now I've not done too many calculations. Okay. But still we have done a few. Then I've got minus t plus t cube by 3 factorial, etc., etc. And then t minus t cube by 3 factorial, etc., etc. And then again 1 minus t squared by 2 factorial, etc. Do you know any power series which start off looking like 1 minus t squared by 2 factorial?
Oh.
Yeah. Sorry, somebody said something.
Cosine, right?
Yeah, cosine, right? So cos t power series starts like this. Now, this is not a clue. I mean, you need to compute more terms or do some induction, see that exactly the right things show up. But okay, from this pattern, I'm just saying, okay, this is really what happens. T minus t cube by 3 factorial and so on are the first couple of terms of sine t, right? And this is minus sine t, and this is again cos t. Okay, so exponential can be done for simple enough matrices, and interesting things do happen. You get some patterns as well. So all these are some indication that using exponential to go from tangent space to the group has the potential for transferring some structure from the tangent space to the group itself, right? If you start with a matrix of a special form, what you are getting is also a matrix of some special form, a different special form, but some special form, right? And so there is some apparent transfer of information from the tangent space to the group itself through this map. Potentially, right? We have to see that it actually moves between the tangent space and the group itself in the first place. But what are things that we can maybe hope to see quickly, all right? So look at these examples. The matrices that I start with may or may not be invertible. For instance, A is 0, then it's not invertible. But this one is invertible, right? Because EA, EB have to be non-zero. This one's invertible too. So is this. It's a rotation matrix. In these simple examples, at least, even though the starting one may not be invertible, the result is. It would be nice to know if this is always true. Now, how could you look at whether it's always true? You could look at, naturally, you'll have to look at the determinant, right? And you'll have to show this is not zero. Okay. All right, now, here's a fun thing one can do, right? What happens? Let's look first at things like diagonal matrices. Okay. In fact, we know the exponential, it is this. Now, what is the determinant of this guy? It's the product of EA and EB. And what is that? That is exponential of A plus B, right? Little a plus little b. What is little a plus little b in terms of the original matrix? It is the trace of the original matrix. Is this pattern holding? Okay. What is the determinant of this exponential? Again, e to the a plus b. Again, that is the trace of the original matrix. This was very different looking. Is it still true? What is the determinant of this matrix? It's 1. What is 1? It's the exponential of 0. What is 0? It is again the trace of the original matrix. So that's very interesting. We can actually conjecture this relationship, that the determinant of the exponential is the exponential of the trace. Okay. And I'll just sort of speak the proof informally. They are proofs by algebra, but let's do a proof by limit and continuity. Okay. So we have already seen that this will work for all diagonal matrices, right? We have seen that explicitly. Now suppose a matrix, and therefore you can prove easily enough that it will work for diagonalizable matrices. A diagonal matrix is similar. Diagonalizable means it's similar to diagonal. Determinant and trace don't change. So because it works for diagonal, it works for diagonalizable. So it's true for all diagonalizable matrices. Now take any matrix, diagonal, okay? maybe it's not diagonalizable, but the point is you can approximate it by diagonalizable ones. Diagonalizable matrices are dense in the space of all matrices. Okay. Okay. So because if you see when is a matrix diagonalizable, one criterion is if you know that if the characteristic roots are all distinct, it will be diagonalizable. Now start with any matrix. Maybe it's not diagonalizable, but by making tiny perturbations to its entries, you can kick around its characteristic polynomial and make sure that the roots are distinct, and then the matrix becomes diagonalizable. Okay, so any matrix can be seen as a limit of diagonalizable ones. Now in this, everything on both sides is continuous. So if things hold for the approximating matrices, they hold for the limit matrix. And so that becomes one interesting way to prove something algebraic, but by using limits and continuity. It can be done by algebra also, but it's kind of fun to see that you need not. You can instead exploit the limits and continuity side of things to prove this. Okay. Now, of course, if I have this cannot be zero, right? Exponential of a real number is not going to be zero, and therefore e to the a will definitely be an invertible matrix, will belong to GLN. Okay. Okay, so let me stop here. But this is sort of confirming thing, right? Because it's taking you into the GLN, right? Which was the big group inside which we are working. So the exponentials do live there. An arbitrary matrix lives in Mn, which is the tangent space to GLN. The exponential lives in GLN. So that is a good observation to have right now. And then we will see that no matter what matrix group you take, and you take the tangent space, the exponential map will go from the tangent space to the matrix group and will always give you a connection between them that you can exploit. So that I will develop in the second lecture tomorrow, and then we will see some benefits of doing that.
Sir, it is determinant of p power a only, right? Minus a is not there.
Oh yeah, no, that was just bad handwriting. But, you know, when I was writing the A in my hands, I mean, you will see other marks in different places. Yeah, sure. But thanks for cleaning that up.
Priya?
Thank you, sir. So let's move to the next session. So it's question and answer session. So if anybody has a doubt, please raise your hand so we can call one by one.
Okay, all right. I also have a question, but I'll wait. Yeah, okay, just go ahead and speak.
So this the domain that you took, I mean, how did you relate tangent space to these matrices?
Okay, see, so, you know, it's not just, okay, let me open another page. The thing is, this is a general idea that take any kind of, say, subset, okay, in some Rn. Okay, it may be a group, it may not be a group, but when it's a group, you will have more facts. Okay, you can talk about tangent vectors to this subset by saying that take any smooth curve that lies purely inside this subset, right? And that is some sigma t. Okay, and if it is smooth, you can differentiate it. Okay, and suppose you are interested in a tangent vector at this point, some point, say p, right? Try it, set it up, and this will pass through some t, but you can always adjust and make it pass through that at t equal to 0. Then sigma dot 0 is what we will call a tangent vector. Okay. Now this is just visualization that this tangent vector I draw as, you know, as if it was here. Right? I mean, actually it should be here, but you always feel free to move vectors around, and you draw it here to highlight the association with this point. Okay, and therefore you could look at other such curves and you could create other tangent vectors. You can always create tangent vectors, but how many, and you know, that will depend on the shape, just how many you get and how they are located relative to each other. It is by no means necessary that they have to form a vector space. They may not. Okay.
Okay.
Okay. But for a group, we can show that the tangent vectors will form a vector space by, well, we did the proof. We showed how to find the sum through a particular curve. Were you asking about this aspect, or you were asking about something about the exponential map?
No, for that exponential map, you took domain also to be subset of matrices.
Yeah, okay. So right now, all we have done is that we have seen that if you work with all n cross n matrices, then exponential takes you to the invertible ones, right? That's basically what we have seen. Okay.
Yeah, but like the two examples that you gave.
In terms of tangent space, okay, so the point is that, you see, suppose you were to take an open subset of some Euclidean space and some point inside. Right? What will be the dimension of, now since you're in an open set, you will be able to move in all directions. In fact, it's very easy to create tangent vectors in all directions because you can simply use straight lines. Right? So you can create tangent vectors in all directions. And so if you have an open subset of, say, Rn, then the tangent space that you create is also n-dimensional. Okay. Now GLNR is, in other words, you can identify the tangent space with the space in which you are working. Same dimension.
Okay.
So what happens with GLNR? Remember, it's open in MNR. So GLNR picture is also something like this. MNR, if I view as Rn squared, GLNR also sits inside it fully, right? Occupying all dimensions as an open subset. Somewhere here is the identity point, and there will be an n-dimensional ball all around it, and you will be able to move by straight lines in all directions. And so again, the tangent space will be the full vector space, the full MNR. You can identify the tangent space with the full MNR. So this MNR can be identified with the tangent space to GLNR. In fact, it's very easy, right? So suppose, let me just do it. So suppose there was, and you just want, there is some point A in GLNR, and you want to generate some tangent vector X, and I want to claim that for anything from here I can do it. What do I have to do? I simply take A plus Tx, right? That is the sigma T that I will use. Okay, and then sigma 0 will be A, and sigma dot 0 will be X. And so everything from MNR will show up as a tangent vector for this.
Yeah, thank you. So
Okay.
one more question.
Yeah.
This, you defined this homomorphism of matrix groups, right? So the second condition was continuity. Can you give some example of homomorphism, which is a group homomorphism but not continuous?
Well, okay. So usually that means doing something funny. Okay. So can you give me, say, a linear map from R to R, which is not, I mean, but linear in what sense, right? So if I have enough of linearity, it won't happen. Okay, so what you have asked me is something tricky, and off the top of my head, I'm having trouble. But it's just making me think of something else. That's a fun thing to think about. So let me put that out there. Can you have a map, not exactly linear, but say at least additive? So it has at least this property, but not continuous. Okay, you can think about this.
Yeah, okay. Think about it.
I don't, it's not reasonable to say, do answer this one right now, okay? I mean, the answer I know is a little tricky, and as far as I know, there is no non-tricky answer to this. So, yeah, so it may not be easy to do what you are saying. I mean, the thing is, all the natural things you would create would always be nice and continuous and smooth and so. You have to do something, especially arrange for things to go wrong.
Okay, sir.
Okay, so maybe
Anyone else?
I had a question for audience in general, because I didn't really wasn't that sure at what level to pitch today's talk. So what I need feedback on, so maybe it's a bit late for that, is like how much of this was already familiar to you in portions at least. So let's take some arbitrary cutoff. Give me a rough answer. So, and you know how to do that through Zoom, right? So you can say yes or no. So if if you would say that 1/3 of this I already knew, then you can click on yes. I'm not seeing many responses. Okay, so I'm seeing, okay, and if your answer is no, then click on no. All right, only 8 responses. There's still more than that left here.
Yes, few people are chatting. In the chat, they don't know.
Oh, I see. Okay, no. All right, so I think I feel okay about my choices. And then tomorrow we'll go on from here. So hopefully if your answer is no, then, but still hopefully what was done was understandable. And then we'll build on this tomorrow. And if you said yes, then maybe hopefully tomorrow you will see more things that you had not seen before. Okay.
Yeah, so anyone else has a question?
Ishan.
No, sorry. I was trying to remove that green tick mark because others had no.
No, I already cleared actually. Yeah.
Okay.
No questions.
This exponential map is actually very, very useful. I mean, you probably, if you've done some differential equations course, you might have come across it there, right? And just as exponential of x is fundamental to calculus, exponential of matrices is very fundamental to anything that you do with matrices.